morning, everyone. I am Tanisha Tyagi from S. Chand Publishing, and it's an absolute honor to welcome you to the third edition of a Grand Mathematics Summit. Last year, over 1,500 of you joined us, making it an unforgettable experience. This year, we have taken things to the next level, bigger, better, and even more inspiring. Today, we are not just exploring mathematics, we are turning it into a love language, a connection that goes beyond numbers and formulas, straight to the heart of how we think, learn, and innovate. And what's better way to begin then, with our very first session on why do we need to make mathematics a love language, led by the renowned speaker, Mr. Sunil Singh, a distinguished author, storyteller, and visionary mathematics educator who has a remarkable ability to bring math to life, with a global reputation for intertwining the rich history of mathematics with modern perspectives. Mr. Singh has delivered over 100 keynotes, presentations, and workshops at iconic venues like the Museum of Mathematics, the Royal Conservatory of Music, and the Italian Cultural Institute. In 2021, he also led a groundbreaking webinar on culturally responsive mathematics for the US National Commission on Mathematics Instruction. Mr. Singh's work with the Number Lab inspires students and educators by showcasing the beauty of mathematics. His upcoming book, Sonic Seducer: Lust for Life with Our Heaviest Moments, Magic, and Memories of Rock and Roll, is set to release in 2024. So, participants, now get ready for 2 days packed with amazing learning, valuable insights, and the chance to win big. That's right, we will be hosting a quiz tomorrow with the winning participants receiving fantastic Amazon vouchers worth up to rupees 50,000. But before we begin, here are a few important housekeeping notes. Participants will be muted throughout the entire session. Please ensure you have a pen and paper to note the important information. The chat box will be enabled during the Q&A round and as requested by the speaker. To receive your e-certificates, please complete the feedback form that will be emailed to you after the final session, that is tomorrow. And be sure to participate in the quiz tomorrow. We will share the quiz link at the end of the final session. Now, without further delay, let's welcome Mr. Sunil Singh to share his invaluable insights. The floor is yours, sir.
Thank you so much. Good morning. It's 12:30 in the morning here in Toronto, Canada, but I stay up late, and so I'm very eager to connect with all of you in the 45 minutes, an hour we have, but also you can always connect with me on social media, email me if you have any questions or want to continue the discussion after this and after the summit. So let me first start sharing my screen. And I'm just going to make sure that everybody can see that.
Yes, sir, it's visible.
Perfect. Okay. So let's begin. And let's begin with the highest sort of illumination of mathematics in terms of why should we make it a love language? Right? It's a question. And this presentation is part of the answer. But I think even just this quote by Galileo, it really lifts the realm of mathematics to its highest purpose and definition. It's invoking the idea of the universe. It's invoking the idea of a God deity, regardless of your faith. That is the vector of mathematics. That is what mathematics is. Now, do our students get to see that? Do they feel that? That's something that we need to work on better. And that's why I think if we make mathematics a love language, like, some people's love language is food, music. Well, why not mathematics? And of course, if we're going to talk about God and the idea of mathematics, then we definitely have to bring in probably one of the, if not the greatest mathematician ever, Srinivasa Ramanujan. Uh, again, it's important to keep it this high because we sometimes think of these ideas, these quotes, to exist outside of education, or they live in books, or they live in history. They have to live in our classrooms. And we are going to get to the nuts and bolts and have actual mathematics. We're not going to have time to do the mathematics, but hopefully if this presentation is shared, you can do the mathematics on your own. So we're going to start with some high level ideas before we get into the language part of it and what language means in terms of fluency. Language. What is the purpose of language? It's to communicate. The purpose of language is to communicate. And every language throughout history, storytelling has been the best way to communicate. We can talk in facts, we can talk in bullet points. But if someone tells you a story in whatever language, it's invoking past cultures, customs, histories. There's an emotional resonance. Stories transfer energy. Stories transfer energy. And if mathematics can be carried in these stories, then that energy is going to come to our students. So I want to, again, talk about almost the science of storytelling. And it goes back, not surprisingly, all the way back to, hunter-gatherer indigenous groups. That's what, because storytelling was so important in terms of who to choose, in terms of partners and fertility. So one of the stories I want to share uh, is by a group called the Agda people in the Philippines. This story isn't very long. It takes 30 seconds to tell. In fact, the story is on the next slide. But I want you to listen to the story, and I want you to listen to why telling a story is more important than giving facts. So the story that the Agda people tell is about a sea cow and a wild pig. They were best friends, and they used to race every day until the sea cow hurt its leg. But the wild pig then carried the sea cow to the water, and they continued racing. The wild pig on land and the sea cow in the water. Story's over. And you can see on the next slide, this was from a New York Times story, 2017, how telling stories makes us human. And that is the story I told, more or less, right? 30 seconds. Now, imagine your classroom if you're asked to talk about these different topics, which are important: friendship, cooperation, aversion to inequality, empathy. The best way to combine them inextricably is through a story. Everything will uh, fall better in terms of permanence. And we want mathematics to be learned with permanence and not be forgotten year after year. So the idea of stories and language, it seems to be a very important part here of how we communicate mathematics. And so we're going to be dealing with, and I should update this slide, this image. Uh, it braids all the fluencies: factual, procedural, conceptual, historical, and contemporary. So the contemporary braid's not there, but I'm going to talk about contemporary fluency. Because if you're going to speak a language, some people, even though I don't speak anymore, I left India in 1969, and I can still understand Hindi a bit. But my mother, who still, says when someone speaks, whether it's Hindi, Punjabi, Urdu, she'll always comment on how well they speak that language. So even though someone else might be saying it correctly, it's the way that they speak it. And I want you to keep this next slide in mind. So if we're talking about language fluency, and I just listed a couple languages which are specific to India, but even English, French, Italian, Spanish. How well you speak that language has to do with all those quotations there. And all those things are transferable to mathematics, to speak it as a language, to speak it as our love language. Because what's the only reason to learn mathematics is because you love it. So let's get into some factual fluency. Okay. I don't know what it's like in India, the climate of education or parents, times tables. We have the same issue here. But let me start with this. 100. I want you to think of the first multiplication fact, an interesting multiplication fact for 100. Now, there's not a lot of choices. I mean, there's infinite if we were to use the decimals or fractions, but for the standard multiplication facts for 100, 10 times 10, 20 times 5, 50 times 2, 25 times 4, and 100 times 1, one of them is actually my favorite, and I think the most unique. And I think some of you might go 10 times 10. It's a square, right? 100 is a square number. It's not 10 times 10. That's not the one that's interesting. That's not the one where we know as much information about. So here's the one that, and it might surprise you, and of course I will tell you what it is. This is the multiplication fact for 100, which is, I think, the most interesting. And right now, before I even go to the next slide, a good marker of mental health, generally the mental health in mathematics, is curiosity. Right now, all of you are curious, I think, as to why Sunil has chosen 5 times 20 as an interesting math fact, right? That's it. That's curiosity. It's a simple thing, but the way I've framed it in some sort of little story narrative, you're curious. Well, let me show you why. You see, if you add consecutive odd numbers, you get your square numbers. And we never think of 19 as the last number of the consecutive odd numbers that adds up to 100. We never think of 19. 19 is a prime. It doesn't feel like it has any other sort of connection, but it does. And the reason why I said 5 times 20 is because if we look at the numbers in a very Gaussian way, 1 and 19 give you 20. 3 and 17 give you 20. 5 and 15 give you 20. 13 and 7, 11 and 9. You have 5 copies of 20. That's how Gauss added numbers from 1 to 100 when he was 13 years old. You know, he did it very quickly. So not only do we get a unique math fact and this idea of square numbers coming out from, but we also get this idea of looking at numbers differently. So factual fluency, this is a fact. But some facts have more color and vibrancy than other facts. So when people say, oh, we need to get back to basics, we need to do facts, absolutely, I agree with them. But which facts are you talking about? Which facts are you talking about? So let me push that argument even more. Here are the times tables. I purposely chose one which was really hard to look at. Like, it's just awful. I didn't want to choose a nice one. I want to choose something which is really, you know, the colors or just, it just seems so off-putting, if I could say that. Okay. Well, there's some numbers, some multiplication facts are more special than others here. A little bit more special. For example, this one. 6 equals 2 times 3. That's really special. And the color coding was intentional. Not for the 6, but for the 2 and the 3. Let me tell you why I chose those colors before I get into why 6 is a very special mathematical fact for multiplication. Some of you might know this. So I got this, this is from Prime Climb. Some of you might have heard of this resource, Dan Finkel, Math for Love, that's his company. Look at the colors for 6. So the orange represents 2. A green represents 3. So every number can be represented with either the primes that build it, or it's prime on its own. So anything which is completely red is going to be a prime. Now, if you look at 8, it's got 3 orange slices, so it's 2 times 2 times 2. So it's a very visual way of kids to understand how numbers break down. It's one thing to see 2 times 2 times 2 times 2, but to see it visually represented symmetrically, I think is much more powerful. So that's why I chose the colors. But there's much more happening with 6. It's a multiplication of an odd times an even. Sorry, even times an odd. Right? Numbers have personalities. Don't just call numbers, every number is the same. that's what gives mathematics its beauty, that these numbers have their own quirks and color and textures. And this is really important. So even just saying it's an even times an odd, and you might think, well, how much can you do with even odd? You can do quite a bit. We're not going to do this here. This is from a mentor of mine, Peter Harrison. This is so important that all these questions, the answers are only odd or even. So every student is going to want to take a risk. If they get the wrong answer, they might go, okay, oh, now I see why it's even. So you can ask rich mathematical questions on factual fluency just based on odd or even. And they're getting a very sort of broad range relationship, how these numbers interact when you're adding them, or squaring them, or the summation of consecutive ones. So important to have a broad understanding how odd and evens interact early on. As soon as kids can sort of understand odd and even, this is very important. So odd and even has even a lot going on. Okay, but this is the beginning of a 3,000-year-old story. Remember, I told you, language for communication, and the most powerful communication is through a story. And this is a story of perfect numbers. So a perfect number is any number which equals the sum of its proper divisors. Proper divisors mean we do not include the actual number. So 6, all the numbers which go evenly into 6 are 1, 2, 3. 1, 2, 3 equals 6. It's a perfect number. And it seems like you multiply it by a binary and a prime. The binary numbers are doubling numbers, 2, 4, 8, 16, 32, 64, 128, etc. And your primes are 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, etc. Does this hold true? Well, let's go to the next perfect number, which is 28. 1, 2, 4, 7, 14 add up to 28. But look at the magic which is coming out here now. You've got 4 times 7, which if it sits in a times table, it's like a peacock without its colors. This is very special. So not only is it a binary times a prime, but it's a binary times a Mersenne prime. So there's a bit of history here. What is a Mersenne prime? Any prime which can be written 2 to the n subtract 1. Sure enough, 7 is 2 to the exponent 3 subtract 1. And then starting at 28, it is also the sum of consecutive odd cubes. It's one thing to be perfect, but this perfect relationship goes on and has all these mathematical things just pop out. The next perfect number, I don't know if you know what it is, it's 496. And all the numbers which go to 496, 1, 2, 4, 8, 16, 32, 16, 31, 62, 124, 248, add up to 496. And sure enough, you're getting into mathematical gold now. And because we know it's going to be a binary times a prime, kids can guess what the next perfect number after 28 is. They don't have to try all these different numbers. Okay, it's got to be binary. It's got to be bigger than, obviously, 4. Let me try 8. Let me try 16. But it's also got to be a prime, Mersenne prime. And sure enough, it's going to be 16 times 31, which gives it to you. And you also have the summation of odd cubes all the way from 1 cubed to 7 cubed. And the next one is 8128, but we have found 51 perfect numbers. That's it, 51. And every time we find a perfect number, we find a Mersenne prime. And there's something called the Great Internet Mersenne Prime Search. We have all these supercomputers linked together trying to find it. And I think they get something $50,000 or $100,000 by finding the next one. But we've only found 51 perfect numbers. And think about it. 6 is perfect. 28 is perfect. 496. That's 3 that kids can understand and see. And then there's only 48 more that have been discovered. So fluency, factual fluency, it can be rich and very deep. And this is a whiteboard of just my work. And I just, on the right-hand side, I listed all the things which came out by teaching perfect numbers. Okay. So because I taught perfect numbers, look at all the other topics which are woven in. And there's some basic sort of computational ideas, but there's also some history in terms of, who discovered them, Pietro Cataldi discovered, like, I think the seventh and eighth, which are into the billions, these perfect numbers, and by hand. He did it by hand. So, what is on the board is a story. It's a mathematical story. And all those things come out just by looking at perfect numbers. And I like this slide because it shows, like, okay, back to basics. Just give me the basics. Okay, 4 times 7 is equal to 28. 5 times 7 is equal to 35. Are you going to treat 28 and 35 exactly the same? Are you going to teach that exactly the same? Because you're missing a whole segment of math history and mathematical beauty, and closer to the idea of fluency and as a love language. So that is the mathematics of number 3. Very sort of psychedelic, like Alice in Wonderland, Lewis Carroll's Alice in Wonderland. And of course, something is beautiful, magical. It makes it into media. The mysterious math of perfection. That, like, it's media, especially scientific media, or is going to tell math stories, which are important, and perfect numbers are important. And related to primes, Euler, he had he's again one of the great mathematicians. He had a hunch, he had a belief that we would never discover the prime number patterning. That was his sort of sense that, what, I don't think this is ever going to be resolved. Now, this is part of something called the Riemann's hypothesis. This goes into contemporary fluency. Do our students know what the unsolved problems in mathematics there are? There's over 1,000. What problems, if they were to be solved, I'll talk about this later, if they were to be solved, how would it benefit society? What is it? What changes would occur? So the idea of fluency in contemporary knowledge, contemporary applications, is also very important. 127 seems like a random number, right? All numbers have personalities and characteristics. And I chose 127 because it's got quite a few personalities and quirks to it. One that you might know about, it's a Mersenne prime. It's a Mersenne prime. You can write it as 2 to the exponent 7, which is 128, subtract 1 is 127. So it is one of our Mersenne primes. It is one of our cherished 51 Mersenne primes. But it's got a little bit more. It's got a weird history, 127. Let me show you what it is. So this is a relationship. We have a binary raised to an exponent plus p, which is prime. And there's a mathematician named Polniak who believed that you could write every odd number with this relationship. Every odd number. Pick any odd number. Of course, he started, except 1. He started with 3. And 3 you can do, because 2 to the exponent 0 is 1. Plus 2 is, and 2 is the only even prime number. And that gives us 3. And you can do 5. I'll just give you an example. You could, like, what 59 looks like. So again, the whole idea is you can write any odd number. That was Polniak's belief. You can write any odd number as a summation of a binary plus a prime. And here it's 2 to the exponent of 4, which gives us 16. 16 plus 43 is 59. This is a great activity to do with your students, especially if you have a large class and everyone gets assigned a odd number. And everyone will be able to do it either individually or in groups. And then you ask your students, what do you want to believe about this, about Polniak's idea? Or what would you like to have a conjecture based on all the information collected that everybody in this class got their odd number as a summation of a binary plus a prime? And kids are going to say, it looks like it works for all of them. That's fair, except it doesn't. So it doesn't, the first number it doesn't work for is outside of 1 is 127. And Polniak, I think, went up to 121 or 123 and stopped. This is a tragic mistake in mathematics, that we assume that a pattern is going to go on forever. And that's why proof is so important. And this is a very a great example to tell kids why proof is important. It's not good enough to have 50 examples. It's not good enough 50,000 examples, as we're going to find out. You need proof. Now, some of this proof obviously is beyond kids, but to have the seed of proof implanted early on is a very important part of the language aspect of mathematics. To speak it with certainty or uncertainty and knowing how to differentiate between the two. So I love this problem because it gets kids to practice some basic, what are the primes, like to know their primes, to work with binary numbers. So there's some, but it's also a historical problem. Okay, so this is a Gaussian graph, which kind of illustrates the uniqueness of numbers. And if you were to share this slide with your students, and they're allowed to pick one number as to why it is categorized as that, only one, I'm going to guess that most students will go, hey, miss or mister, why is 70 weird? They will ask the question. They will ask it. That's the beauty. They'll ask it. When questions are asked, voluntarily, that is a good math question. So they go, okay, everybody want to know why 70 is weird? Let's talk about why 70 is weird. And I actually found this birthday card. Someone turning 70, that's so weird, right? So 70 is called a weird number. Why? That's the curiosity again. Do you tell me that with the word weird, that there's going to be students go, yeah, I'm not interested. I don't want to know why it's weird. Look at the word, the word weird, right? That itself is going to invoke, okay, well, how could 70 be weird? Doesn't look weird to me. It is weird. So again, just for sake of time, I would actually have this activity because it would take a long time to actually figure out why it's weird. And I have to give you a lot of sort of suggestions or ideas. So all the proper divisors of 70, there they are. Okay. 1, 2, 5, 7, 10, 14, and 35. I think I've got them all. And they add up to 74. Okay. They add up to 74. And you think, okay, that's not that interesting. Well, if you go back to the previous slide, anything which has a sum of its proper divisors more than number is called an abundant number. So the sum was 74, and because this sum is greater than the number being examined, it's called abundant number. Okay, but there's nothing weird about that, except there is. You see, and I got this slide back here, usually, almost all the time, you can find numbers from the proper divisors to add to your number. So for example, 12 is abundant, and you can use some of its proper divisors to add up to 12. 6 plus 4 plus 2 gives you 12. 6, 4, and 2 go into 12. Try to make 70. You can't add up to 70 with any combination of 70's proper divisors. That's why it's called weird, because even though it has an abundance in terms of all the sum, you can't build 70. And so hopefully one student's going to go, yeah, Mr. Singh, wow, are there other weird numbers? And this is where you go, I don't know. And even if you do know, say, I don't know, because they're going to explore. They're going to Google weird numbers, and they're going to find out the next weird number is 836, and there's an infinite number. And they might find out about other kind of numbers, like amicable numbers or social numbers or primitive numbers. Or that's the point of having rich mathematics, because if you have the direction where it has this language aspect of higher levels of fluency, you're going to have higher levels of interest, curiosity, and discussion. Procedural fluency. What's that? Well, I think we know what it is. And I'll give you a very straightforward example of procedural fluency. So if you're asked to solve for x, the algebraic steps, and I won't go through them, but there's a procedure. You recognize an algebraic equation. I have to isolate for x. You'll go through the the equitable, correct algebraic operations done to both sides eventually until x is isolated. That's procedural. But there's a conceptual understanding here too. If I cover up that entire root and you just show that to kids, they're going to go, that's got to be 8. The cube root of 8 is 2. That's correct. There better be an 8 underneath there. And that's a very good way of looking at it. There's got to be an 8. So you tell everyone, okay, it's got to be 8. Okay, it's got to be 8. And if it's not 8, then we have to look at something else. And then you start to do this. And they go, oh, well, it's still got to be 8. And you go, right. So whatever's behind my yellow sticky, which is shrinking, it's got to be 3. Right? This is the conceptual understanding of what's going on. So you're going, okay, it better be 3. Well, it's not 3. It's a square root. So kids are learning some facts along the way, but there's a conceptual binding happening here too. Okay, well, it's got to be 3, but I need a 3. Oh, it's got to be 9? Yeah, it's going to be 9. And eventually you get into this idea of solving for x, right? Which is going to be 4. So there's an algebraic procedural, but there's also a conceptual understanding of what's happening here in the big macro sense. And that equation I showed you is not something of what Keith Devlin is saying here, but I want to bring in again the idea of the highest power, the idea of the something like the essence of love. When he's talking about a Shakespearean sonnet, this is a very high level thinking of mathematics. Of course, it's a very special formula, Euler's equation, Euler's identity, but it's where we have to move all our students. This is the equity part. All our students are capable of this kind of inquiry and curiosity. So here's my simplest proof for the need for storytelling fluency. Simplest proof. I don't know if you've seen this slide before, but this is the checkmate move in chess. So if people are going, yeah, I don't know if I've got time for storytelling, I just need my kids to do, this is where you can just say, this is why we need to do storytelling. So this was a poll done in the United States. Should schools in America teach Arabic or Hindu Arabic numerals as part of their curriculum? 56% said no. Do we need to go through the irony here? If we, and I'm not talking about in India, but I'm talking about, let's say, in Western countries, especially the United States and Canada. If our students and teachers don't even know where numbers come from, then what are we doing? Like, what's the point? If you're not going to have, and this license plate, this a great question would be, especially in maybe kids in North American classes, but maybe classes in India too. Show that license plate, because up in the upper left you have the Hindu Arabic numerals, and the lower right you have Eastern Arabic. Ask kids, okay, which of these numerals are Hindu Arabic? And I bet you most kids will point to the Eastern Arabic, especially Western kids. They're going to think that those are English numbers. Okay, Angrezi. How's my Hindi? This is very disturbing. So let me give you an example where we braid in factual, procedural, conceptual fluency with a very special number, 0, which, as Indians, we should know its origin. So look at this question here. 2 subtract -5. Now, we do this question all the time. It's like 2 minuses make a plus, 2 plus 5 is 7. No, don't do that. They're getting the correct answer, but there's no understanding. So what you do is you say, I'm going to add 0. Because adding 0 does nothing, right? So the first thing when they see 2 subtract 5 negatives, they're going to go, I don't know how to do that. I don't even have 5 negative to withdraw. talk in language, talk in proper, like in terms of subtraction is a verb. Negatives and positives are objects. If you speak proper language, there's better understanding. So you add a zero and you say, the kids go, well, that's going to do nothing. Exactly. It's going to do nothing. But now you get into zero pairing. So now you go, well, I wish I had 5 negatives to a draw. I don't. But if I have 5 negatives plus 5 positives, that is a form of zero that I can use to help me answer this question. And sure enough, if you have the same number of objects, subtract same number of objects, you get zero. And what are we left? We're left with just the residue of 2 positives and 5 positives. And that's going to give us 7. Now, you're not going to do this question every single time like this, but I think it's a moral imperative to go through it with this kind of fluency. This is Jonathan Crabtree, who's spent a good portion of his life trying to understand why the West completely dropped the ball on Brahmagupta's understanding of zero, because he was an astronomer too. And his book Brahmasputha Siddhanta, I don't know, there's like 23 chapters. Maybe the West didn't read the chapter on why zero's got to be the lowest number. You can't have less than zero energy or matter in the universe. You can't have less than zero. Everything else, positive, negatives, has quantity. You would never say an electron, which is charge -1, is less than a proton, positron, which is +1. You would never say that. So that's why kids get confused with positive negatives. Maybe the number line should have looked like that. So we have to stop teaching the false story. This is maybe not the narrative in India, but in the West, it still could be like this. I'm Indian. When I went to school in Canada, I didn't know too much about Indian math history. I just assumed it came mostly from who told me it came from. There's no attribution of people and stuff like that. So we got to stop doing this. So I have one last question, because we're going to do some Q&A. I usually spend more time on this question. So if you're allowed to take 1 or 2 steps, how many different ways can you get up 8 stairs? So you're allowed to take 1 step or 2 steps, and you must always be going forward. So whatever your total is with 1s and 2s, it must add up to 8. Okay, so you have to climb 8 stairs, 1 or 2. You can't go backwards. One student asked me, "Can I go backwards?" I go, "That's a brilliant question," because if you're allowed to go backwards, there's infinite ways to get up these 8 steps. Always going forward, always positive. So what I did is I gave some examples. These are all the different ways to climb up the 8 steps, right? They're all different. The arrangements of 1s and 2s are different. Even if something might have only 1, 2, it depends on where you took that jump of 2, right? So I know some of you might be thinking, oh, this is permutations and combinations. No, it can go that way, but what is the simplest way of doing things? This is a question which could be tackled by young students. Right? I mean, we might go through the brute force, like, okay, let's try to get all the examples down, but you're going to duplicate, you might miss one. You might be able to get almost all of them, but as you get closer to the right answer, it's going to be hard to know which one you're missing unless you really categorize it. But brute force is a really good first step. But there's a more elegant way. If you actually start with the simplest scenario, which is a very important strategic tool of mathematics, to always start with the simplest case. Start with 1 step. Well, 1 step, it seems trivial. It's just one way. With 2 steps, it also seems trivial. 1, 1, or 2. 2 ways. 3 also seems trivial. There's 3 ways, right? But when you get to 4 steps, it takes a bit of a jump. It goes to 5 ways. And if you have 5 steps, there's 8 ways. And some of you might be recognizing these numbers now. 1, 2, 3, 5, 8, 13, 21, 34. And you might say the Fibonacci numbers, because you had the 2 previous numbers to get the next. Well, I'm hoping I'm hoping as an Indian audience, you're not saying that. Because you should know that the person who discovered these numbers prior to Fibonacci and Leonardo of Pisa was Hemachandra, about 150 years earlier. So now they're called the Hemachandra, Fibonacci numbers. That's fine. It's not a race. It's not a competition. We don't always choose what came first. I mean, look at how information was communicated at the time. It's not a race. Every culture, civilization which has discovered it should be rightfully attributed. But we always learned it through the Fibonacci numbers, right? Always. And even something like Pascal's triangle. Pascal was at least the sixth person who discovered it. The first person who discovered that relationship of the numbers in the triangle was a Sanskrit poet, Pingala, about 200, 300 current era, or was BC, I forget, but he was the first. And there have been other people who discovered that triangle. And again, speaking of the triangle, speaking of having really a fluency of the triangle, I don't know how many of you know this, Newton's expansion. This was standard when I went to high school, that the triangle of the patterning exists outside the diagonal rows of one. And you get to the binomial expansion in terms of infinite geometric series. That was standard when I went to school. That's not taught anymore. In fact, if you try to Google this, I had to take a picture of my textbook. You can't even find this information on the internet anymore. We're losing our language. So I think this is a really we're getting close to. Well, actually, no. There's a couple more things I want to talk about. I've got 5 minutes, maybe 7. We have to start teaching the proper story of mathematics, and this is from Crest the Peacock, George Avisi. First edition came out in 1991. There's 3 editions now, and this is, if you look at where Europe came in, right? And Europe's very important, but look at all the other cultural civilizations, especially India, in terms of where mathematics came from, where mathematics intersected. Most of high school topics in North America, it's mostly 9th century Indian mathematics. If you look at trigonometry and quadratics, except for statistics and calculus and some other topics, most of mathematics was discovered by Indian mathematicians. So the last one I'm going to get to, I'm going to get through this very quickly because I want to have some time for Q&A, is contemporary fluency. It's what do you know what's up to date? So let's do it this way. So I've done this activity, and I do it slide by slide. So the first thing I go, it's not possible for 0. Okay, so not much information. Not possible for 2. Remember, this is something which is contemporary here, but this is my very cryptic way of going about it. It's possible for 4. It's 2 plus 2. Again, I want students to figure out what's going on. So someone might go, 6, 3 plus 3. Oh, okay, hang on. They're just even numbers. 8's going to be 4 plus 4. It's possible for 8, but it's 3 plus 5. And I've also color-coded, if you remember correctly, right? So this is actually a girl I tutor in Italy. So by the time it got to 16, she figured out what was going on. She said, these even numbers can be a sum of 2 primes. That's the conjecture. That's the Goldbach conjecture, that every even number 4 and above can be written as a summation of 2 primes. Hasn't been proven. It seems like it's true, but hasn't been proven. And the last thing I want to leave for you, because we're getting close to it, just turns out, but we can't trust patterns as much as we want to. So I've been with the Polynax numbers, but what algorithm would have predicted that Kamala Harris would have become vice president in 2020 based on the previous number of vice presidents? There is no correlation. So we have to be very careful about patterns. So the last one I do want to share, and I'm definitely going to end it, is first give you a definition of relatively prime. So relatively prime means 2 numbers like 7 and 20 who don't have any common divisors in common except for 1. That's it. They don't have anything in common. That's what relatively prime means. So this one looks really strange. Picking number n, and n to 17 plus 9, and n plus 1 brackets to 17 plus 9 are relatively prime. So pick any number. I mean, if you were to put in chat, everybody's number would work. Everybody's. Whatever number you can think of, put in chat, it would work until it doesn't. And it doesn't up until this number. I can't even say this number because it's so big. I don't even know how many illions it is. But it works up until this, and then it fails. And that's the beauty of mathematics. And that's why I'll leave you with this last quote, because we started with Galileo. The sun, with all the planets revolving around it, dependent on it, can still ripen a bunch of grapes as if it had nothing else in the universe to do. Those grapes ripening is that previous example of, like, who would care about that? Somewhere it becomes not relatively prime at a number that we would not think about. What was the point of that? Same way with the ripening of the grapes. So with that, I would like to conclude my presentation and definitely look for some Q&A.
Participants, if you have any questions or queries, you can post it in the chat box. We'll take up the questions one by one. Miss Nirmala Kumar, CMA, I can see you have raised your hand. So if you have any question or query.
Is there a question? Okay. Let's see. How does it work to get the questions?
Participants, if you have any questions, please drop your questions in the chat box. The chat box is open for you.
I wonder if they
Okay,
can
so
unmute.
yeah, there's one question. How teaching history of maths relevant in math class?
Well, I think if we don't teach math history, then we're going to teach some concepts incorrectly. We're going to give false attribution of discoveries. We're going to, as the case with zero, the West is adopted as a placeholder. It teaches negative numbers 5 years after positive numbers. If we don't teach math history, and you can teach math history without math history, but you're teaching a very soulless version of mathematics. So yeah, you can absolutely, you can teach it, but the story of mathematics is so beautiful that it's humanizing. So if you're taking history out of it, you have to at least say that it's dehumanizing, that it's simply just these inert numbers that interact without having any history of who interacted with them and their struggle, their confusion. So students can have some empathy as to that's what I'm going through too.
So there's one more. How we connect this topic with primary students?
Well, primary students, I would definitely they're the ones who are the most curious. So even just having questions about odds and evens, that's a fluency which is very important. What is the relationship with odds and evens? If you add three odds, three evens, four odds, four evens, let them discover what the rule patterning is going to be. It's very safe because it's based on just odds and evens. Having kids know their primes. Of course, they'll know what primes as they get older, but I think for primary students, knowing the primes 2, 3, 5, 7, that's a good start because they'll know that those numbers, no other number goes into them and can be divided into except the one and itself. And maybe they can discover the next prime number. They can play around with 9 and 10. Oh, nine's not prime because 3 goes into 9. Oh, 11, nothing goes into. So maybe have kids discover prime numbers too.
Okay, so there's one more. How do you deal with challenges of completing the grade-wise syllabus curriculum since we want to do so much, but there is so little time?
Well, that's a very good question. That's a reality of almost every teacher. Um, and you have to balance it. You have to balance what's best for your students. You also have to, of course, there's a curriculum you have to address. But a lot of these topics, especially with our rich topics, they have, I think that's the problem with the curriculum, that all the topics are separated, they're disconnected. But if you do something like number theory and explore number theory, a lot of the things that we want kids to be able to do, adding fluency, multiplication fluency, working with powers, that's braided into the problem. But I think the first thing is that you recognize, okay, I've got a curriculum, but I don't got time, but I want to teach it this way. I wish I could have time to put these puzzles and problems in. That's a first step, because that's your own sort of uh, moral rudder, which way to go. Now, as a teacher, and this is just me, I didn't care about the curriculum. I cared about my students, because I knew my students were going to get a richer math education than if I went by the curriculum strictly. And that was a trust factor. And sure enough, men finally realized these kids are learning more mathematics. But that was just me as a teacher. I was quite rebellious.
Okay, so there's one more. How can we relate a real life event to square root and cube root to make children understand the concept?
Repeat the question, sorry.
How can we relate a real life event to square root and cube root to make children understand the concept?
Well, I think the got to be very careful here, because I think always drawing things in the real world, that's where I think kids, like squaring and cubing, uh, mathematics is an abstract language. And sometimes it has real world applications, a lot of times. But if we start selling it that way all the time, we're going to start to create really false. Look at all the trigonometry applications. If you're to throw three coins on the ground, they're going to form a triangle, not a straight line. So then to create these questions about applications of trigonometry, no, that's not genuine. So just the idea of squaring and cubing maybe have problems in terms of or what even the square looks like. A square is a square. A cube is a third dimension. So you can actually talk about shapes in terms of what a cube is. But I think the real life, you have to be really careful, because if it's not a real life application or as much, you have to be honest, yeah, intellectually honest. And if it's a question where there's a lot of applications, a lot of applications.
Okay, so there's one more. Can you tell some motivational facts about math so that students start to involve them in self maths class and make their favorite subject?
That's an excellent question. It's very important, because every student is different in the classroom. So every student's going to have their own individual uh, relationship as to why they like math. And this goes back to where some kids might like the practicality of it, like in terms of working out percentages, or calculating uh, you know tax and groceries, and like all the practical aspects, saving money and all that kind of stuff. That might be appealing for some students. For some students, it might be something which is related to art, uh, someone to history. Someone loves history, and there's a lot of history in mathematics. So we have to start teaching mathematics as an interdisciplinary subject, that it crosses over into the languages, it crosses over into science, it crosses over into history, it crosses over to poetry, technology. So we have to get better at this. I'm not saying anyone is really good at this right now, but if we're going to address that question with all the different kind of students in our class, I think it's important that we start teaching mathematics almost like humanities, almost like humanities.
So, can you suggest a book to understand the history of mathematics?
Oh, the one I would definitely is the Crest the Peacock, George Javisi Joseph. So Crest the Peacock, non-European roots of mathematics.
Okay, is there any repository of activities, puzzles, games, etc., that can make teaching learning of math interactive and fun?
Yeah, I would definitely go to Mathagon. It's a free website. Go to Mathagon. It's a free website, and if you go to their Polypad, which is a interacting, visual manipulatives, it's got a lot of puzzles, tanagrams, really concrete representations of things we want to learn. Very fun, very playful, really good use of technology and mathematics. So it's called Mathagon. It's a free website, and I'd highly recommend it.
Okay, there's one more. Some students are slow learners in math because of less interest. So, can we make a balance in class?
Well, I'll be honest, most kids should hate math because the way it's taught. I'll be very blunt. Uh, most kids do hate math. Uh, Even the ones who are good at it can't wait to drop it. So we have to change the way we teach it. Um, because the way we teach it, I mean, I was good in math, but history was my favorite subject. So we have to be very careful about, especially with young learners, we have to involve them with their questioning. They have to feel like they can bring something to the table, like whatever it is, and for them to ponder questions. And it's not important to have the answer right away. If it takes 3 or 4 days, it's okay. It's okay for kids to be confused or disoriented or lost. These are natural emotions. So having those conversations are very important because right now you got to do math and you got to be correct. And if the more time you take, the weaker you are as a student. Mathematics is about slow failure. If you look at the history of mathematics, it's about slow failure. And what do we do in school? We teach fast success. So we got to be more attentive to history, and that's why we got to teach mathematics through a lens of history.
There's one more. How do we connect it in class with 21st century syllabus? Uh,
Well, I think again, 21st century means some people might go STEM, science, technology, education, engineering, mathematics. Sorry, but it's interdisciplinary. Like we have to start to have kids who might not even like mathematics because the discussion maybe it's on climate change, maybe it's on data science, um, uh, polls. When there's elections, why can we, do these polls with this kind of accuracy? Read the newspaper, anything which has numbers to discuss numbers. Are these numbers? Can we take them at face value? Is there something like start looking at social media in terms of their usage numbers. So I think there's lots of ways to develop interest, which is related to what kids are doing and seeing with the internet and social media technology.
so there's one more. Do you have a suggestion of some mandatory topics or classes to be taught in middle school?
Well, middle school. I would definitely have kids by that age have a fluency of prime numbers. Um, some other stuff about number theory, like perfect numbers. Um, they should have a good uh, sense of estimation, that they should be able to estimate what the answer is going to be to a computational problem. So the power of estimation should start coming in middle school. I think they can start developing algebraic thinking, much like that problem I showed, where you can look at it conceptually and procedurally. I think it's quite for kids to start to have a sense of what balancing an equation looks like and doing that thing in middle school. So, and I think middle school is very important too, because they're still very curious. They're not going to be weighed down by some of the expectations of high school and later. So I think middle school getting sound arithmetic skills, really sound arithmetic skills.
Okay, thank you so much, sir. Thank you for your enlightening presentation on why do we need to make mathematics our love language. You have brilliantly highlighted that mathematics, often seen as technical and dry, is the key to unlocking the universe's secrets. And thank you to all the participants for joining us today. We hope you found the session both informative and inspiring. So, participants, this is a quick reminder that our next session, Importance of Positive Parental Involvement in Math Education, is scheduled for 12 p.m. today, 12 noon. So, let's meet there. Stay tuned for more sessions filled with rich discussions on various aspects of mathematics. And don't forget, tomorrow we have an exciting lucky draw and quiz with Amazon vouchers worth up to 50,000 up for grabs. See you at noon. Don't miss out. Thank you, Sunil sir. It was a wonderful session. Thank you so
Thank you so
much.
much. Thank you.
Have a good night, sir. Thanks a lot. Thank